Cool. So should I intro?
Yeah, sure.
Okay,
Thank you.
cool. All right, yeah, thanks for coming out this week, everyone. Today, I guess we have two speakers, which is a unique sort of I guess occurrence for the for this series. So we have Sikata Sengupta and Marcel Hussing, both from UPenn. So Sikata is a PhD student where she's advised by Mike Kearns, Aaron Roth, and Duncan Watts. Is that right?
Yes.
That's a big trifecta, and is interested in, I guess, broadly speaking, on like ML, algorithmic games theory, RL, and control. And then Marcel, who I guess will be joining us shortly, also at UPenn, like I said, is advised by Eric Eaton and works kind of at the intersection of reinforcement learning and algorithmic stability. And yeah, today they're going to be talking about Oracle efficient RL with max value ensembles. Kind of a new perspective, I guess, on like sort of different oracles and benchmarks for RL. So I'm excited to see the talk, and I guess Sikata will take it away.
Thanks so much, Dylan. So yes, I'm Sikata, and Marcel will be joining us shortly, as Dylan just said. And today we'll be presenting joint work with Michael Kearns, Aaron Roth, and Jess Sorrell on Oracle efficient reinforcement learning for max value ensembles. All right, so in tabular MDPs, we know that we have access to computationally and statistically efficient algorithms like Rmax or E-cube, which enable us to learn near optimal policies. However, in many real-world or more realistic settings, we often need large, if not infinite, state spaces to tackle the problem, and there we find ourselves posed with the following challenge. Either we can incur size of state space dependent lower bounds, or we may have to make strong structural assumptions in order to get these statistical and computational guarantees. The video is playing for everyone, right? Just to confirm. Awesome. Okay, so one such example of a large state space that we'll also revisit later on in our talk is in the context of robotics and this robotics arm. So we might imagine in this setting that our state space is encoding things like the positions of all the joints of this arm and also perhaps the velocities at these joints. And you could also imagine it encoding things about the actual cube and its positions and its velocities. So right off the bat, we have this very large and continuous state space. Now, you might imagine the actions in this setting as being like the application of forces to such joints, and we might think of tasks here as being things like we may have some path on this platform that we are interested in moving this cube along. However, as mentioned earlier, if we wanted to give theoretical guarantees of the ability to learn an optimal policy here and have all of these efficiency guarantees, we would have to make some strong assumptions about the underlying MDP that models this process. All right, so with this in mind, we asked ourselves, what if instead of aiming to compete with an optimal policy, instead we aimed to compete with a slightly weaker benchmark? And so with this motivation in mind, we considered the following setting. Suppose we had access to K base policies that form some base policy class. We make no assumptions about how these policies were collected or how they were gathered. So presumably they're suboptimal and maybe slightly better in different parts of the state space. They could have been gathered in a heuristic manner, or, to be quite honest, they could just be leftover policies from other similar experiments run, and we just have a haphazard class of these policies put together. So one natural notion of how we might consider improving upon this base class of policies is via max following. And max following asks us that at every state, we're going to select the policy from the base class whose value function is maximum. So for the purposes of just warming up, we're going to consider a scenario where we perfectly know the value functions of this base class of policies well, but of course, this is not very feasible, especially because we're in a large state space. So after we walk through this example, we're going to talk about our set of relaxed assumptions down the line. All right, so let's first start off with this toy example where we just have two policies, pi 1 and pi 2, we could imagine partitioning our state space into the regions where v pi 1 of s is greater than or equal to v pi 2 of s, and into the region where v pi 2 of s is strictly greater than v pi 1 of s. So without loss of generality, we might imagine that our starting state is in S1. And since our value functions are perfectly known for the time being, our max following policy would choose to select pi 1 from this region S1. And now at each subsequent time step, we may transition into a state that is in S1, but at some time step, we may ultimately transition into a region where now we are in S2, where v pi 2 of s is better than v pi 1 of s. So at this time step, we can now consider two scenarios. One in which we just continue committing to pi 1 that we played from the beginning, or we can now consider, upon crossing this partition, whether we should now switch and play pi 2 from there on out. And I think in this example, because of the way we design these partitions, the value functions are giving us the signal that in expectation, playing pi 2 upon switching across the partition is better for us. So intuitively, we can kind of build up over time these comparisons of scenarios, one in which you commit to pi 1, one in which you do one switch, playing pi 2 when you switch the partition, and so on and so forth, if you were to cross back into region S1 and back and forth. And we think about this max following policy as kind of being some way of facilitating these switches and proving to us that you can do no worse than the base class of policies. And I think it's worth mentioning that there's many ways of proving in the case where we have perfectly known value functions that the max following policy can't do worse than the base class. But we kind of choose to present it along the intuition of this switching argument because it kind of helps us reason about some of the things in our setting down the line in this presentation. All right, so before we proceed to describe the main setting that we'll consider in this paper, there are a number of works, I would say, that are considering ensembling in RL or improving upon a base class rather than always competing to try and learn an optimal policy. So here we mention a few of those papers, but our paper refers to many more works that exist in the area. So I'll try to describe kind of like a high-level overview of the aims of some of these works, and then I'll mention some few differences between the setting that we're going to consider and what these papers do. So to start us off, Cheng et al. Are interested in a setting of imitation learning with multiple oracles, and they're broadly interested in questions where you may have multiple suboptimal experts that are giving you conflicting advice at different states. So in their paper, they're also interested in competing with this baseline of the state-wise value function maximum of the base class of policies. But in their framework, they solve their problem by doing a reduction from their policy optimization problem to one of online learning. And then they reason about this one-step look-ahead style max aggregation policy and show it's competitive with their base class of policies. So two primary ways in which our paper will differ from the setting they consider is that first, they primarily focus on an online learnability assumption, whereas we're going to entirely be focused on a batch learnability setting, as will be talked about down the line. And the second is that rather than taking a value-based approach, they're primarily focused on policy-based approaches. And we know that in certain cases, policy gradient methods risk challenges with either stability or higher variance. And so the work of Liu et al. Builds on this Mamba algorithm by adding in an active component, but at its core, it's still different from us in a similar means of this online learnability and policy gradient use case. Another line of very cool work is by Burrito et al. On generalized policy improvement, and they are broadly interested in problems around transfer learning in RL. So they consider settings where you may have tasks that share this underlying joint successor feature representation, and they use this to show that if they learned policies under tasks with this representation, when faced with a new task that also shares this representation, they can efficiently generate improvement using these old policies on this new related task. So fundamentally, they kind of differ from us in the MDP representation structure that they assume and the way their tasks share this joint representation. And finally, Brukim et al. Consider boosting NRL, and they are actually able to compete with the optimal policy. However, in order to do so, they have to make a stronger weak learnability assumption than we will make in this paper. So with that, I will hand it off to Marcel.
Yeah, hey everyone. Sorry for being a bit late. The thing that maybe you should know about me is that I'm mostly coming from an empirical background, and I only started doing learning theory like a little while ago, so I've been involved in some of these papers. But the thing that I thought was really cool about this is, right, we want to assume that so Sikata so far talked about that our value functions are known. But the thing that we really want to assume is that our value functions are not known, but instead we have some mechanism of obtaining them. And more precisely, what we want to assume is how we started this project really was we wanted to say over the past 15 years, the deep learning people have gotten really good at solving supervised learning problems, while the deep reinforcement learning people are still struggling with these challenges that come from data distribution shift and off-policy learning and all these kinds of issues that you encounter when you throw your neural network at some Q-learning algorithm. So we wanted to take a step back and essentially say, well, we know how to solve supervised learning problems, so why don't we use that fact and see what we can do in RL? So there's been this like maybe disconnect between like what theory we do in RL and what we can practically implement. But using these types of oracles that we're going to use now, we're going to be able to reason about the theory of these algorithms while maintaining the ability to implement things on interesting, at least to me, interesting tasks. And what we're going to do is we're going to eventually show that we can actually implement this algorithm on robots. So that being said, let's look at the assumption that we're actually going to make. Okay, so to get into the setting a bit, most people here are probably familiar with it. We're looking at an episodic Markov decision process with state, action space, reward functions, and so on. And the results will state in terms of stationary rewards and transition dynamics, but you can easily extend those outside the presentation. And what we're going to assume is that there's a set of policies, pi k, it's missing a k. At every time step, we're going to select one from, as Sikata mentioned, and each of these policies is associated with a value function vk. That is just the regular value function that you all know, just conditioned on using the specific policy out of the k subset policies that you have. And the assumption that we want to make is an oracle assumption. So I said before, we want to assume that we don't know the ground truth value function, but rather we have the ability to obtain a value function, and that is like good in some sense. And good here means we want to have a squared error guarantee against the ground truth value function of some policy. So we're going to be able to say that given some sampleable distribution, so we're going to need, and this is denoted mu here, there's going to be some distribution that I can draw samples from. And on this distribution, I will be able to obtain a low squared error guarantee. And this is the supervised learning problem that I talked about that we hope we can solve. Now, this oracle assumption recently was studied by Galovic, Moitra, and Rohatgi. And I think you guys had a talk about this like maybe a few weeks ago. That talked about this work, where essentially they show that in a specific class of block MDPs, this type of oracle is insufficient to learn an optimal policy. So really, we know we can't get an optimal policy, but with this set of policies as a base class of policies, can we do better than before? And so far, we've covered a bit of warm-up. We've talked about, related work and what our oracle is going to look like. I'll talk a bit more about some examples for you to get an understanding what this max following thing is. We'll introduce a benchmark class that we're going to need for the proofs, and I'll talk a bit about the algorithm, and then Sikata will show you guys some math that everyone's probably very excited about, and then I'll show you some robots that hopefully everyone is excited about. All right. Let's look at some examples of this max following thing to convince ourselves that this is a good idea to do. So imagine this MDP where you have 3 states and you have 2 fixed policies given to you. One policy can always go right and one policy can always go left. And any state where we don't denote an arrow with a reward, that just means you stay in the same state and you don't get any reward. So if I'm in state S2 and I pick the policy go right, you just stay in S2 and you don't get reward. Clearly, if I pick any of the fixed policy and I just execute it indefinitely, I will either get stuck, I'll get stuck in the tail ends, either in S0 or in S2. But if I was smart enough to do policy 1, then 2, then 1, then 2, and I switched between them at every time step, I would essentially get H reward. And if we assume that our maximum reward is 1, so rewards are between 0 and 1 is common, then we'll get actually an optimal policy by combining these two. Okay, so now I'm going to show you that it's unfortunately not always true. It would be nice if it was, of course. But same example, we're going to have a policy that can go right. We're going to have a policy that can go left. And we're going to have a policy that can go up. Suppose you started in state S2. What would our value functions for each of these policies tell us? Well, the value of going left is you always get 0, so that value is 0. The value of going up is always 0, so you're going to get 0. The value of going right is epsilon, so we should do that. Now, the problem is if we were a little bit smarter, we would have somehow ended up in state S4, where we could have gotten a lot of 1s of reward. But unfortunately, with this type of approach, we won't. So clearly, we can't always get an optimal policy. Let's highlight one more thing in this MDP. Let's look at S0. From S0, I want to highlight that tie breaking is important. Any of the value functions, left, right, up, would have 0 reward. Note that in S1, there's no arrow to the right, so the right policy would actually not reach epsilon, right? From where we are here. In S1, you would just stay in S1 if you took the right action. So all the values are 0. But suppose I got lucky, and smart as I am with my luck, I actually picked the right policy first. And then because all the values are 0, I have to tie break somehow. I'm just going to pick the right policy because maybe I can get lucky. And then I'm going to pick the up policy afterwards in S1. And all of a sudden, I'm in a state where I have a high value. Had I picked a different tie breaking rule, we would have ended up with a very different policy. Okay. So let's we talked about approximation. So let's look at an example where approximation comes in and where it relates to what we just talked about. So now we have 2 policies, red and blue. And again, if you're in some state, there's no arrow. That just means you stay in the state and you get 0 reward. And we want to start in the state S0. And according to the rewards, what the value function of the blue and the red policies would tell us, you would first take blue, go to S2, then you take red, and then you stay in S3 indefinitely. Well, that's great. But our oracle assumption said, well, your value estimate's actually not going to be perfectly accurate. So suppose my value estimate actually told me the value of going to the right, taking the red action in S0 is actually alpha, and alpha is larger than epsilon. Now I would go right, and I wouldn't obtain this optimal policy that the true max following policy would yield. So we have to be a bit careful in how we handle approximations. And the last thing, here's one MDP that kind of pains me to call an MDP. At the x-axis, you have the states, and all the transitions basically let you stay in the same state. You're actually not transitioning at all. There's going to be 2 actions, red and pink, and there's going to be a reward function associated with the y-axis. And what you can see here is that the 2 actions correspond to affine value functions. And the combination, the max following policy, however, would be piecewise affine. It would be the combination of, get this V, You always pick the largest value. And this kind of shows us that even though our base class is like some lower dimensional parametric form, the max following policy that we will never have to actually represent can be from a much richer class. So imagine these are not linear functions, these are like base neural network policies. I can represent an even more complex function by simply combining them. Okay. So now we have to kind of introduce some notation because we want to talk about these approximations and how they're going to come in our algorithm. So instead of talking about max following policies, we'll talk about a class of policies that we'll call approximate max following policies. To do so, let's define a set of beta good policies at every state sh. You select from your set pi k the policy such that the true value of that policy minus some beta is such that the value of the policy is larger than the true value of the largest value in your class minus some beta. And based on this, we can now define a set of approximate max following policies that will simply say, well, for all h and all s, pick pi such that you have some pi t in your class of beta good policies. So there's going to be a larger set now, and let's look at one of the MDPs. Visualization of this thing. For those who don't like math, I figured there's not many of those here. But suppose you have some policy pi 4 that corresponds to the maximum ground truth value. There's going to be some policies that achieve values slightly lower, namely beta lower than this, in this case pi 1 and pi 2. And then there's some threshold pi 3. So pi 3 would not be a policy that we would want to use in our benchmark class. Now let's look at this MDP. So now, depending on approximation, if I start in S0, I'm going to get different max following policies. Namely one that, for instance, always goes left. That would be a max following policy because of my error. And the approximate max following class would actually contain this policy. So this policy would be part of the benchmark class that we're going to be interested in. Okay. Then we can state the algorithm. The algorithm goes in rounds, iterate over all h, and then iterate over all possible policies that you have. You're going to have the sampleable distribution mh, which might be a simulator that you can run. And then you have you sample a starting state from the starting state distribution. You execute the current max following policy that you have so far estimated up to state h, and then you call the oracle on the next state. And then you iterate and build up your max following policy over time. And then in the end, you output the corresponding policy that takes the argmax of the VK that you build up. So that's the algorithm. And now we can look at some of the theory of like why this algorithm actually works.
All right, so broadly, we try to break down our theoretical results into two main components. First, we show that the policy outputted by our algorithm is epsilon competitive with the worst policy of this benchmark class that Marcel just told us about. And then for the second part of this argument, we show that this worst policy of this benchmark class is epsilon competitive with the best policy from the base class. All right, it's not moving next. Did the next slide show up for everybody? Okay. All right, so more formally, for the first part of this result, we show that the expectation, according to state samples from the initial distribution of the value of the policy outputted by our algorithm, is epsilon competitive with the worst policy from our benchmark class. Because, as Marcel said, in our algorithm, we make a loop over all time steps and over all experts. We make O of HK queries total, and we select our beta as for our benchmark class parameter to be theta epsilon over h, and our alpha that's used as our regression oracle parameter is theta epsilon cube over kh to the 4. All right, so to prove the first part of this result, we define a set of bad states as a state such that any policy in our base class has estimated value function error larger than epsilon over 2h. Then we can define a set of bad trajectories as trajectories such that across any time step, we have a state in that trajectory that is a member of the set of bad states that we defined in the last round. All right, so just at a high level, the broad way we'll proceed in proving this is that we will relate the policy that our algorithm outputs to an approximate max following policy from this benchmark class for good trajectories. And then what we can do is bound the contribution to the expected value of the policy outputted by our algorithm in terms of the components from good and bad trajectories. And then we will compare our performance with that of a worst approximate max following policy and bound the probability of getting a bad trajectory using our oracle assumption. So we'll walk through this more slowly, but this is just the outline of what we're going to do. All right, so the first thing we want to show is that for good trajectories, the probability of generating some trajectory tau prime under our policy is equal to the probability of generating it under some policy in our approximate max following policy class. And to do this, what we'll argue is suppose we start at a state at some round h and we're in a good state because we're considering good trajectories. We can call k star the index of the policy selected as the best of the estimated value functions at that state. And then because we're at a good state, we know that the true value of that k star policy is within an epsilon over 2h of the estimated value function of that policy. And then by the way we define this k star, we know it attains the maximum of the estimated values. And then because, again, we're at a good state, we can relate it back to the true values of the base class at that state and have an order beta term. All right, so now just to tie it together, we will break down the contributions of the value function of our policy into the good trajectory and bad trajectory terms, which we can lower bound by the contributions from the good trajectories. And now because we're considering good trajectories, we can relate it back to this approximate max following policy because we related those two distributions for good trajectories. And now we can again lower bound this by the worst value of h, because our rewards are bounded, of the bad trajectories. And finally, because we have now related it to some approximate max following policy, we can compare it with the worst approximate max following policy. And what remains to be done is to bound the contribution from the bad trajectories probability. And so to do this, what we'll ultimately do is we'll connect back the probability of generating these bad trajectories to this probability under our policy from our algorithm. And we can upper bound this with a union bound over at any time step the probability you land at a bad state. And because we have our oracle assumptions over these distributions generated according to our approximate max following policy, we can bound the probability that any of the base class of policies have a larger than epsilon over 2h approximation error. And then we can union bound once again over all policies and horizon steps. So we get an order epsilon over h error term. All right, so just to recap, the first part, this was all to show that the policy outputted by our algorithm max iteration is epsilon competitive with the worst policy of this benchmark class. And so to tie this all together, the second part of this result will now show that this worst policy of our benchmark class is epsilon competitive with the best policy from the base class. And to do this, we're kind of going to come back to this switching argument intuition that we talked about at the beginning. So a procedure that we're going to reason about is we're going to consider running our approximate max following policy for C steps and then committing to whatever policy we chose at that state SC at time step C for the rest of the episode. And what we're going to inductively argue is that this procedure of following it for C steps and then committing can't do much worse than following the best policy from the base class. So very loosely, the inductive step that we're going to try to prove is going to be to show that if we broke down our cumulative rewards into the regions where we followed the max following policy for C steps, and then we played and committed to the policy at time step C at state SC for the rest, we can't do worse than order epsilon C plus 1 over h from the best policy from the base class. All right, so you already saw this notation on the last slide, but we're going to define pi t of sh to represent the policy from the base class selected at time step h from state s. Okay, so once again, that's what we're trying to prove. And for the base case, we already know, because we're working with an approximate max following policy, that from whichever state S0 you got, the policy selected by this approximate max following policy is within beta of the max of all of the base class of policies' true values. So we automatically basically get that our base case holds. And now for the inductive step, we want to show that if we assume this follow this procedure following for C steps, if we follow it for C+1, we only get another order epsilon plus h addition to our competitive argument. So we get order epsilon C+2 over h worse than the max of this base class of policies. And to do this, so we'll start again on assuming we follow the max following policy for C+1 steps and then commit. And then we can rewrite that in terms of the value function. And because we're working with a base class policy, we know it's epsilon over h competitive with the true baseline of the max of the base class of policies at that state. And now we can reason that this is lower bounded by whatever policy was selected at the last time step, because that was only taking into account SC, whereas we know that the policy we selected was, was at least, if it's with a true baseline, we know that it attains it. So we can lower bound this by the policy selected at the last time step. And then we can rewrite this now, expand out the cumulative rewards in terms of the policy selected at the last time step, and you'll see that this restructures itself back in terms of our inductive hypothesis, and we just get an additional epsilon over h contribution to our error. So just to recap this, we showed that the worst approximate max following policy is epsilon competitive with the base class, and together we've related the policy of our algorithm to the base class of policies in this breakdown. And now I'll hand it over to Marcel for some experiments.
Actually, wait, can I just ask a quick question?
Yes.
Actually, wait, can you just go back to like the main sort of guarantee?
Or like this one, or the first?
Yeah, just like the main sample complexity guarantee for the algorithm.
Okay, yes.
Yeah. No, sorry, I just wanted to spend a little more time like just parsing out the like alpha and like the beta and stuff. And wait, so alpha is the precision for the oracle, right?
Yes, so it's the assumption for the base class of policies squared error.
Yeah, okay, cool. So I guess yeah, okay. I was just trying to I was just double checking. Yeah, so so this is like poly 1 over k, which I guess like makes sense. So like sample complexity is poly k. I guess you can't avoid paying for k, right? Like even if it were horizon 1, you would kind of need to pay for k.
Yes.
In the worst case, right?
I think even with her. Yeah.
Yeah, cool. So then I guess like the cool thing is that indeed it's like, when we increase h, there's maybe like, well, in principle, far more than just k kind of like policies we're playing with, but we're only paying like hk and not like
exactly
or something like this. Okay, cool.
Exactly.
All right. Yeah, thanks. Okay, yeah, I just wanted to like spend a little bit more time parsing this.
No, thank you for highlighting it. Yeah.
Okay, good, cool.
Okay.
All right,
I'll go to robot arms now. Oh, oops. Okay.
All right, finally, robots. So the thing that we motivated this whole thing with, to some extent, was this idea of we want an algorithm that we can put on some real world task in some sense. And the setting that we're going to choose here is a setting where you may have policies lying around from previous projects that you did where you trained your robot to do certain things. So suppose maybe you trained your robot before using, maybe some standard RL to sweep the floor. And now during that training, your robot learned how to move and how to move the broom and how to sweep. And then the second thing that you did at some point is you taught it how to bring out the trash. And now, it knows how to bring out the trash and how to sweep the broom. And what we would like to do is we'd like to use what we already have lying around in terms of policies and try to learn something new. Maybe in this case, we want to learn how to wash the dishes. And this notion is kind of encapsulated in a benchmark that we published a few years ago. So if you go to the next slide, we can look at some of the actual tasks. So there's a robot arm here. This is an EVA arm. And this arm has to pick up this object.
Hmm.
Can you just hit the next slide button again?
Oh, wait. Yeah, it's not playing.
Is there a play button? And we can skip it. There was a nice, cool video of this. I was so excited to show this.
I can hang on. I'll pull it up on my end and I'll share. But yeah, I have the video is yeah. Okay, Marcel, you want to keep explaining and then I'll
Yeah. So basically, how this benchmark works. This benchmark consists of 4 different axes. There are robot arms, objects, obstacles, and objectives. And for each of these axes, you have different elements. So there are going to be 4 different robot arms. There are going to be 4 different objects, where each object requires different type of handling. So there's going to be a dumbbell, for instance, which can only be picked up from the side, while there's a box that can only be picked up from the top. So they require different types of manipulation behavior. And the nice thing is you can plug and play them together as you would like. So you can just pick one of the robot arms, pick one of the objects, and can construct a task like this. And that gives you exponentially many tasks. So by 4 axes with 4 elements, we're going to have 256 different combinations of tasks that we can pick from. For the sake of this paper, we fixed the robot arm. Oh, there we go.
Okay. Here.
Yeah.
This is playing.
So you may have a robot arm that moves this object, and then you could imagine switching out the robot arm. So rather than just having 1 robot arm, we have 2 robot arms. And then maybe there are different tasks. So rather than picking and placing this, you're now pushing the object. Or maybe it's not actually a box, it's a plate. You can pick up the plate and have to pick and place it or push it. And maybe then there's an obstacle in the way. So there are different obstacles that block off the object from the arm or the object from the goal in different positions. Cool. Exciting. Okay, so here at the top, you see all the different combinations kind of laid out. And we're focusing on a scenario where the robot arm is going to be fixed for now. And the obstacle is like the no obstacle, just for the sake of simplicity. What we're going to do is we're going to train on 2 tasks. So there's going to be 2 constituent base policies. And we're going to try to take a new task and combine our 2 policies to solve this new task. Okay. So there's going to be policy 0 and 1 in the legend here that are the base policies. And there's going to be IQL, which is a reinforcement learning algorithm that's trained on offline data and then can online fine-tune to some task. And then there's going to be our max iteration algorithm. So let's focus on the leftmost plot first. At the top, you see it says dumbbell, pick, place, box, trash can. These are essentially the tasks that we trained on initially. So take the dumbbell, pick and place it. Take the box and drop it in the trash can. And the arrow then indicates the next task that we want to do is take the dumbbell and put it in a trash can. In the plot, what you see on the leftmost legend, you're going to see the returns, or the leftmost, the Y label. And then on the right, you see the success rate, which is indicated by a little red bar on the plots. So the leftmost plot, we see that both base policies, policy 0 and policy 1, achieve 100 return, roughly. The fine-tuned policy, the online learned, that's pre-trained on some of this data and then fine-tuned on the next task, is the orange line. It doesn't really do much better. And the cool thing here is combining both policies using our algorithm not only gives you a lot more reward, you now actually solve the task. You can actually 20% of the time or something, 10% of the time, solve the task completely where previously you couldn't. Now, the next plot, we go to a different task. These are different task combinations now, just to highlight different behaviors of this algorithm. We're starting with a policy that's already kind of getting success in this task, which is policy 0, and one policy that's not getting success. Again, fine-tuning just kind of retains the behavior of the first policy. Combining them, all of a sudden, you get almost 100% success rate. That's really cool. well, the last thing that we need to show is if you have two policies that are not very great, then our algorithm can't give you an optimal policy. We already established that. And in these cases, you may get more reward than you did before, but we don't get any success. That all being said, now you might ask, okay, why is this fine-tuning baseline doing so poorly? Like, why is this thing not like? The reason is because the whole motivation for this work was sample complexity. And the amount of data it requires to get the blue bars is around the order of maybe 10 rollouts per policy. The number is incredibly small. And that is the cool thing. So I only need to run my robot like 10 times. If you have ever trained an online RL algorithm, we're talking about like thousands of rollouts. If you have some knowledge and you can reuse it, this gives you an amazing starting point to do so. And I think this is pretty cool. And yeah, to be clear, how does this algorithm work? It's basically the max iteration algorithm that we implemented before. And for our oracles, we simply plug in a neural network that needs to solve a supervised learning problem of approximating the value of the current policy. And it turns out on-policy evaluation with neural networks isn't that difficult, as opposed to off-policy training.
So wait, do you use like rollouts to do the evaluation, or like do you just regress onto like returns?
Yeah, pretty much.
Okay, cool.
Yeah, okay. So that's experiments. So let's recap. What have we seen? Well, we first looked at this algorithm and this oracle assumption that we've been working with, and we kind of proved this theorem using this structure of the approximate max following policy class not being much worse than, or being better than the base policies. And then we looked at some how this combination in practice can give us some cool results even on the robot while having theoretical guarantees. That being said, there are open problems, and one thing that Sikata has already worked on with some people that sometimes attend here as well, I believe, is our current algorithm only works. It assumes that we have a distribution of a start state. So one question might be, what if you have an adversarial start state distribution? Could you still get guarantees of this form? And some other things that we haven't worked on is, okay, what are other techniques that you could combine your value functions, and when do they buy you what? So one idea might be, is it ever sensible to do softmax ensembling rather than just like maximum value ensembling? I think one question that bugs me a lot is like, what types of policies do you need to get conditions for optimality? And like, right now we have the statement we're greater than or equal than the best policy in the class. When does this thing become a greater than, and not a greater equal? And I think that's a super interesting question. And then the last thing that we've been thinking about a bit is, can you kind of relax this notion of oracle maybe, or can you think about like calibration on the base class of policies rather than like these oracle assumptions, and what would that buy you? Yeah, that all being said, there's a bunch of really cool work that we wanted to highlight of other people that have worked in this area. And these are things that certainly have inspired some of the stuff that we thought about. You should check them out. There's much more in the paper, much more interesting work, of course. But overall, that is it for this presentation. So we thank you very much. And if you have any questions, feel free to ask.
Nice. Let's give a round of applause. Oh, wait, I need to remember how to do it. There we go. Cool. Yeah, I thought that was a great talk. And you guys also did a very good job of like seamlessly switching between the two parts. Very engaging. Yeah, I mean, I think definitely the question of like when is it like a strict greater than is like that's like obviously like a super fundamental one, right? Because like, if you just wanted to compete with like the best in the class and you're willing to pay with K, then like obviously you can kind of just like try each one out and see which one is the best. But then like clearly, I mean, especially if you look at the experiments, like clearly the algorithm is doing like better than that benchmark.
Right.
So that's pretty cool. Yeah, I guess there were questions. Wait, Drew, did you have a question?
I think someone else raised their hand.
I'll open.
Oh, okay. Was it Sujit? Did you have a question?
Oh, yeah.
Do you want to mute?
Sorry, I was trying to clap hands and.
Oh, no worries.
Oh,
Then I guess I did have a question.
cute.
There's the you had this like choice of like which robot arm in the data set that you didn't explore. Like, would you have to sort of generalize this like framework of value functions and stuff if they're like using sort of differently parameterized action spaces, or have you thought about that at all?
So that's kind of one of the reasons. Well, in this case, okay, to be quite precise, in this case it wouldn't matter because they're all 7 DOF arms, and like, the action spaces have at least the same shape. But yeah, that is in part one of the reasons why we were thinking about fixing one arm, right? Especially the kinematics of like one arm versus the other might change quite drastically. And you need policies that can be executed in like the same space, so to say, right? Like if you don't have that, you need to think about how to do that. And yeah, that might make things more tricky, and you might not necessarily need an extension, but you need like a value function extension from a concept perspective, but you need a way to translate one policy in the other, right? You need to be able to say this policy does this in that space, but it does this in that space. So there's possibly like an extension where you just like expand your state space to some extent. But in practice, that seems a bit more tricky than I make it sound in theory.
Yeah, I guess I wonder if there's some way of like aggregating like the features they've learned somehow instead of like aggregating.
That is a fantastic question.
Yeah, we're very excited by that question.
That's a good one.
Yes. So I think there are a couple of really cool questions. That is one of them. Like this idea of like, do you have different feature spaces? Maybe they have some
Yeah, like,
underlying structure.
how do you get
how
to-
can
yeah.
you get something that is like more expressive than what we currently have?
Yeah.
Super interesting.
Yeah. If you want to chat more, we're like very excited about that direction.
Sure. Yeah.
Nice. Let's see. Were there any other questions from people in the audience? I can ask one right now. Maybe this is obvious. Sorry, this like just kind of like came to me, but like if you think about like tabular RL. So like, we know you can like learn in your optimal policy here with sample complexity. It's like, poly in, horizon, number of states, number of actions. This is kind of related to the question of like, when is it a strict greater than, but like, is there a natural choice of like the base set of policies here that allows you to compete with like the optimal policy if you're in the
Right.
tabular set?
So you guys are all touching on questions that are like have like haunted us or been our source of motivation for a very long time. So like I can tell you in the case of this selection of base class, we were, for example, in the case of like linear quadratic regulators, we were like, oh, like if we chose policies that acted along certain axes or like certain dimensions, there might be a way that max following actually shows much closer to optimal performance. So we were inspired by notions of like sufficient diversity or like dimension along which these policies are acting in order to get something better or competing with optimal. But we have sort of characterized, I guess, in like different types of MDPs, some of the properties that are like in our left-right example, that diversity is letting us get an optimal, but like we don't have one nice all-encompassing set of descriptions that let us say under these other conditions it would be better.
I think there's maybe an obvious statement to make that is, at any state, there must be one policy in your class of policies that takes the same action as the optimal policy.
Right.
That is something that must be true. Now,
That's
from
true.
here, we can think about, okay, what does that mean for the value? Maybe you can make a statement that's slightly tighter by saying, well, not only must that policy be in that class, but also that policy must have the highest value at that state. And from here, we need to think about like structure, I think. It might make sense now to think about structural assumptions on these types of things. And yeah, one thing that I've wondered, from here on, I don't have more to say about this. Like, I think that there's like certain like somewhat trivial statements that we can make from which you might be able to kick something off. The thing that I've wondered, and this is why I at some point I think mentioned to you, Dylan, this idea of like, can we just run 1,000 policies in parallel?
Yes.
Like, maybe that's something that we could do. We could just like get a lot of policies, and if we have sufficiently many policies, maybe then we get something that's like better, at least in practice.
Okay. Yeah, I mean, that makes sense. Yeah, the LQR one is interesting because one thing that's funky about that, this is related to like the left-right example, I guess, is like for LQR, I guess if you do it in the reward setting, so you like, you flip the sign, right? So it's like minus
Right.
quadratic, right? If you're doing it in rewards.
Exactly.
Then like the optimal value functions should be concave.
Right.
But if you like say start with a bunch of linear value functions and then take the max, this generically is going to go towards being like convex rather than concave.
Yeah, exactly. Yeah, we had some very interesting surface plots where we were explaining this, but I do have them.
Yeah, I see. Yeah, so that's
Yeah.
interesting.
Yeah, but yes, like we did have show this for the base class and then the max following with simulation what the surface of that looks like.
I see. Cool. Oh yeah, is there a question?
Yeah, yeah. So one of previous questions was about discussing the evaluation of the policy. So a general way is to basically roll out the policy and see how is it performing. But something was discussed around regressing the policy. So can I know what does that mean, regressing a policy?
Oh
was it-
yeah, I think this was referring to the training. So you have to have some way. Our algorithms still collect some data in the environment, right? And the first thing that you need to do is you need to collect some data in the environment first. And the way we do this is, we don't exactly do what the algorithm suggests. You basically uniformly sample at random an index between 0 and h. You roll out your max following policy, and then that you currently have, and then you roll it until the end to collect data. And then you need to regress something. You need to update the actual value functions to implement the oracle. That's where the regression happens. So if you've ever implemented any deep learning algorithms, that's just
it's giving training basically.
Yeah, at evaluation time, we just roll out. There's no regression happening.
Okay. Oh, yeah, I see. Yeah. Thank you.
Cool. Let's see. Were there any other questions?
If not, maybe I can turn off the recording. Okay,
sounds good. Well, maybe we should give one more round of applause then.
Yeah.
So
thank you very much, Marcel.
Excellent talk. Yeah, it was a really, really good job, both of you.
Thank you.